This film is about the Nuffield approach to the teaching of chemistry. As with the other subjects in the Nuffield Science Teaching Project, the reappraisal of both syllabus and examinations has resulted from widespread dissatisfaction among teachers themselves. Dissatisfaction at having to spend too much time getting pupils to memorize facts and not having enough time to develop in them a real understanding of the subject. The film sets out to give an insight into the spirit behind the Nuffield approach and some idea of how it can work in practice. But it should not be looked on as a perfect copybook demonstration. The teacher in the film applies the Nuffield approach in his own individual way. Filming took place in 2 ordinary classes as things actually happened, with no rehearsals or staging. There has, of course, been a considerable amount of editing, which may make things look easier for the teacher than in fact they were. Finally, it should be stated that pupils taught by this method will not have to take examinations designed merely to test their ability to remember facts. They will take examinations designed to test their ability to think about chemistry. In fact, their real understanding of the subject.
Sit down very quickly now, come on. Now you've heard a little of what chemistry is about. You've also now seen lots of the apparatus and materials we're going to be using. But please remember that most of the apparatus we're going to use and most of the materials are either delicate or dangerous. Never handle them without permission, and when you do handle them, take care. Now, if you want to start doing experiments, you've got to learn to use some of the apparatus. The first thing we're going to use is this, and you all have one in front of you. Now, who's seen one before? Who knows what it is? Hoskin?
It's a Bunsen burner, sir.
Yes, that's right, it's a Bunsen burner. And the first thing I want you to do is to light one of these. I want the first 2 boys from each bench to come up and light a taper.
This is how any chemistry curriculum might begin. To the teacher, it's a familiar world. But what of the children coming to chemistry for the first time? Who can tell how strange it might appear to their eyes? In a strange world, how does a child learn?
Come on, darling. That's a clever boy. This way. Come to Mummy.
It learns the hard way.
Careful.
But what is the learning process? The question may be elementary, but significantly, it's the subject of basic scientific investigation.
I have to play here for a few minutes while I finish some work.
Experiments observing many children have now verified that one of the most important factors, something we all know they possess, is curiosity. child has been under observation here before and is used to playing with the toys. Only the box-like object is new. His reaction is a classic one. Curiosity tempered with caution. But curiosity wins, leading to uninhibited exploration. Because the box produces effects which can be seen and heard, curiosity is kept alive, so further exploration takes place. Things learnt in this way will be remembered by the child. We know that the factors isolated in that experiment are those at work in the everyday behavior of children. A child grows, but curiosity and the challenge of new experience remain. He proceeds through trial and error to cope with new situations more and more successfully. The basic instinct, curiosity, is the teacher's greatest ally. In stage 1 of the Nuffield approach, which takes up to 2 years, the curiosity of these 12-year-olds will be used to make a guided exploration of the visible world of chemistry.
Right. Now, what do you see?
It's turned silver, sir.
Turned silver. Would you say it's silver? Take it out of the flame for a moment. Have a look at it. What do you mean by silver?
It seems to have gone red. Orange.
There's obviously a lot of changes going. What happens if you scrape that with that?
Let it go pink.
Do you think that's something that's formed on the outside or what? What's happened here?
Well, I think it's like formed to prevent the copper inside from burning.
Well, what do you think's happening then?
The film's forming.
The film?
It's giving you something out.
Giving something out? You think this is coming from inside the copper? Do you?
Yes.
Yeah, what?
Combining with something in the air to form the film.
So you think something in the copper is doing what?
It's coming out. Well, it's combining with the air to form that film.
Yeah. What do you think?
The same.
You think the same? Well, what do you think? You tell me then, since you say you think the same.
I think there is something coming out and combining with the air.
Something combining with the air. Do you think you could think up an experiment to see whether the air is important in this or not?
Yes, well, if you...
Well, I don't want to hear it yet. I'm going to ask you all in a moment when you're lined up round the bench. All right?
Right.
Okay. Gosh, you soon had none left at all. I didn't know. Oh, all right.
Scraped it off, sir.
Well, what about it then, Pearson?
Oh, sir, it got coated with a film, but
Yes.
it's something on the copper, the top layer of
What
copper.
makes you think it's something on the copper?
So it gets thinner when you scrape it off.
Yes, it scrapes away. Yes.
Yes, sir.
Well, where do you think it's coming from, this black colour?
The heat.
From the flame.
Yes, sir.
Think it's something coming out of the flame?
Yes, sir.
See whether you can think up. You think it's coming out of the flame. Do you think it's coming out of the flame?
I think it's coming out of the copper, sir. Something
You think it's coming out of the copper? Oh, look, see whether you can think of things you could do, another experiment, which would show which of you is correct. Anyway, look, think about it. I'm going to have you up round the bench in a moment. Right then, we've got 3 theories as to why the copper turns black when it's heated. Now, we've got Solly's theory, which has 6 supporters saying that it's something coming out of the air. We've got Pearson's theory, with 4 supporters saying that it's something coming out of the flame. We've got Deuce's theory, with 18 supporters saying it's something coming out of the copper. Now, obviously, you can't all be right, And you've had some time to think over and work out an experiment to help verify your theory. Okay then, Solly, what's your experiment?
Well, to prove my air idea, it'd be a good idea to put a piece of copper foil in a tube and put a cork in one end, and then take the air out of it with a vacuum pump, and then heat it. If it turns black again, it will prove our idea was wrong. But if it doesn't change, or just melts, our idea will be right.
Good. Do you agree with that, Trumper?
Yes.
Good. Now, what do the flame people think? What do you think, Pearson?
Use another sort of foil, and if that turned black, then you'd know it was something in the flame. But if it didn't, it wouldn't be something in the flame.
Yes. Any idea what particular foil?
Lead foil.
All right, we might try that. What about Gray? You got any ideas?
The same one, sir. Use aluminium, sir.
All right, well, we'll try it. But can anyone think of a way by which they could heat the copper so that the flame won't actually come in contact with it? What could you do to stop it? Any other ideas from this group?
So you could put copper foil in a test tube and then put the test tube over the flame, and the flame won't be getting at the copper.
Good, that's a good idea, isn't it? If you heat the copper in something where the flame's not actually touching. Right, Deuce, now you're the spokesman from the copper school. Now, have you got any ideas on this?
Well, you could repeat Solly's experiment, and if the copper turned black, that would prove us right. But if it stayed as normal, it would prove Solly's group wrong as well.
Right, this is Robert's experiment. Now, you've heated what?
Copper.
In the test tube. What's happened?
Well, it turned black, but got the film on it.
Do you think that black's come from the flame then?
No, sir.
No, it couldn't have done, could it? Okay, right, now let's have a look. Hello? What happens when you heat lead?
Sir, it melts straight away.
Does that tell you anything?
And it's not the flame, sir.
Whoa, does it tell you that?
Not really, sir.
No. Never mind, we can try it at least. Right?
In the flame?
Right, Gray, what about this one?
No black film on it, sir. It seems that it doesn't come from the flame, sir.
There's no black at all? Well, it certainly looks as though it hasn't come from the flame then. Okay, good. Well, what's happening?
Oh, no change.
How quickly did it change when you heated it in the air?
Well, it almost immediately.
Almost immediately.
There's some kind of change, isn't there?
Well, Deuce, are you feeling cheerful or not?
No, I'm not so sure about it now.
You're not so sure. What about Solly? Do you think your theory might be right then?
I'm not quite sure yet.
Well, it might take longer. I think it's something to do with the air.
What about you, Solly?
Feeling very happy, sir.
You're right?
I think
It's certainly staying nice and bright, isn't it? I think you're right, yes. It looks as though your idea about it coming from the air is correct.
These children want to explore. It involves groping and fumbling, making mistakes. But learning the hard way is how judgment is developed. They're also learning that it's proper to have ideas, whether they're right or wrong, but that it's essential to test them. But from this point, they're going to start wanting to know why matter behaves as it does. And this is going to involve them in new ideas about their familiar world. Abstract ideas about molecules, atoms, and ions. These ideas are the concern of Nuffield Stage 2. But how are they to come to grips with? How are they to understand what they can neither see nor touch? How except through the imagination? Like curiosity, imagination is always there to be tapped. In a class of average 14-year-olds, imagination may not be very apparent. Yet a few years earlier, it was visibly at work.
Bang! Do you want a cup of tea?
In the games they play,
Why?
children are imaginative. But what we're interested in is to develop a disciplined, purposeful use of imagination, even with the youngest children. The mature development of this creative imagination, so essential for the artist, is equally essential for the scientist. There's the classic example of Kekule's vision of the structure of benzene. Imagination and discovery converging on each other with dynamic effect. If the imagination can be stimulated, can the young mind also begin to grapple with the most difficult and abstract concepts in science? Here, in the disciplined use of imagination, is the purpose of Nuffield Stage 2.
It's a transparent window with a pattern of thousands of dots on.
Like the light was split up into patterns, the little pinpoints, as on the picture on the card.
Yes. What about this? What do we call the patterns? Can you remember?
Diffraction.
Diffraction pattern. Good. From the pattern we saw, we were able to predict what pattern there was on the card. Why couldn't we tell what pattern there was on the card just by looking at it? Shiraki.
The holes were so small you couldn't see the holes.
Well, yes,
in
the
the window.
pattern was so tiny that by looking at it, did the hand lens help?
No.
No. Even with a hand lens, you were unable to see the actual pattern. But by seeing the diffraction pattern, you were able to tell me what the original pattern was. So how can we sum up? We can say that these diffraction patterns enabled us to what? Forecast what? Wilkinson?
The shape of something that we couldn't see before.
Yes, it enables, well, not the shape, the actual, you're on the right track. Shape, the Barker.
Pattern.
Well, yes, the arrangement of the dots. We were able to forecast what arrangement there was from this large diffraction pattern. Now, you've all looked, I hope, at that background reader by Bragg. Now, what did he do? Wisby.
He used X-rays to look at the structure of crystals.
Yes, instead of using light, he used X-rays. Why did he use X-rays? Any idea?
Because they could penetrate opaque crystal layers.
Yes. And what do you think, House?
Because X-ray rays are, the waveband is smaller than the light rays.
And what did they find? Yes.
Some of the X-rays were reflected off from each of the crystal patterns, and you could see the form of the lattices.
Well, you're saying crystal pattern. What did he actually see?
He saw a diffraction pattern.
Yes. And here, in fact, is a diffraction pattern taken of aluminium. Now, Knight, can you pass these along fairly quickly? Now, remember, this is taken in black and white. Does it remind you of anything? Anyone?
Yeah, when we was looking through the windows in the cards.
Yes, it's very similar. It's not identical to any of those, obviously. It's much more complicated. And so the Braggs were shining these, or directing these X-rays onto crystals, and taking a photograph of the pattern that came off. And this is a photograph of the pattern. From that pattern, they're able to build up an idea that aluminium has a structure similar to this. What are you actually looking at here? What are you looking at? Come on, just tell me what you're looking at. Everyone ought to be able to tell me what they're looking at.
Pattern of the molecules.
Well, you're being too clever here.
There is a round ball, sir.
He's looking at series of round balls, and what's on the outside of them?
Black.
Well, some paint, yes. But you're not looking at an actual crystal, you're looking at a model of the crystal, and this is obtained by studying, amongst other things, that pattern that you've got there. I think the next thing to do, then, is to try and make some crystals of metals.
In this series of 3 double periods, dealing with one of the most challenging topics in the syllabus, the structure of matter, we can see what happens when the imagination is aroused.
All right, what do you see?
It seems to be crystals covered by a green kind of a moss.
Yes. What about the solution?
Oh, it's gone from turquoise.
It's gone green.
Gone green. Why do you think it's gone green?
It's to do with the copper, sir.
Could be. What about the copper? Is that green actually copper or what? Well, do you think it's the silver, the nitrate, or the copper causing it to go green?
Copper.
The copper. Yes. What's happened to the copper?
Well, it's gone into it's mixed with the nitrate.
Yes.
And copper nitrate's blue, I suppose.
Hmm.
Like the crystals we saw being formed on the micro projector.
Yes, they seem to be flake shaped.
Flakes. What about, suppose you look at just one flake. Do you notice anything about it? Does it look evenly grey all the way over?
No, to this side it's a bit lighter.
Sort of patchy grey.
Yes.
Hmm. Right, so you've seen crystals growing in the test tube. Now, let's have a look at this. Piece of metal. Any of you seen metal that looks something like that anywhere? Colby?
On bars and stuff like
On?
Bars.
Bars, yes. What's the word they use for that? Anyone know?
Galvanised.
It's been galvanised. Yes, it's been galvanised. And you can actually see these little pieces. Now have a look at these and see. What does it look like?
Crystal.
They look like crystals, yes. Since we've been talking about these metal crystals, it might be a good idea if we try to represent some. If we use these polystyrene spheres to represent atoms, we can carry out an experiment to try and see the way that atoms might be arranged inside a metal crystal.
Seem all equal.
Yeah, look at that, and that, and that. Well, can you imagine it? Supposing these were little tiny spheres, and there were millions of them. What would you have on this here? What would it look like?
Just an ordinary surface.
What do you mean by an ordinary surface?
Just like this, like a plain side.
Just a plain side. It'll look, in fact,
Solid, all joined together.
and so you can see how the crystals build up. Yes. Good, that's going well. That's it. Now, if you look at it from the side, so you're looking at the bubbles at an angle, what do you notice there?
They all try to stay in a straight line.
But do they succeed?
No, not very often.
See whether you can do a sketch, just drawing lines for the same line, all right? Okay. All right. Now try the other one. Not so easy.
Can't do it.
All right. Anyone else like to have a try at that one?
How can't you be?
Right, bearing in mind the work we've been doing with the bubble raft, I wonder if you could give some explanation why one Colby can bend easily and the other he can't bend at all. Maynard.
Perhaps as the structure of the atoms, as in the bubbles, the lines going like that, blocking the pressure on the outside, blocking it. Could it be that the pattern of the atoms are all going in different ways, like in the grain of a wood, and it might have been very much stronger?
Yes, Harris.
As the grain moves, like that,
Yes.
when he moves it, sees it move like that, but as the other ones, could be all over the place, and the pressure probably pushing one up and some along and down.
Good, yes, but why do you think, House?
In one, the structure was all over the place, the hard one, because you couldn't move, you had difficulty in bending it. The other one was a coarse grain. There wasn't somewhere
it wasn't going all over the place so much.
Good. In other words, which of these two diagrams are you suggesting? This one here or this one here? For the soft one, the one that's bent easily.
Oh, that one over there.
This one here, yes, I think that's a reasonable suggestion. Right, for homework this week, I want you to draw those sketches showing the grains from the bubble raft and explain the bending of the two metals in terms of these grain structures. All right? Right, off you go.
I was doing the bubble raft. You know, you see lines. You just realise, you just think as the bubbles are being, say, the metal magnified millions of times. I picked up the bar. You know, it's terrifically hard. I couldn't bend it at all. Well, I wondered if it was me at first. You know what I mean? I wondered if I was just not strong enough to break it. But when another kid tried it, you know, I realised that that was just the point of the experiment, to show, you know, the different way of structure could change their properties completely.
And we've seen these various forms of sulphur. Here's the flowers of sulphur we started with. Here's the roll sulphur. Here's the rhombic crystals that one of you made. Now, scientists tell us these have all got the same shape, this sort of shape, where each one of these polystyrene spheres represents an atom. How do you think they found this out? Shiraki.
By shining X-rays through the crystals.
Good, and getting?
The diffraction pattern.
Good, from Bragg's work, in fact. Now, we're going to prepare another form of sulphur, so I want the 4N boys, first of all, to come out and collect test tubes, and then the second 4 to come out and collect some sulphur.
Although we've had to condense these 3 double periods, something of the potential of these children to make disciplined use of imagination has been apparent. And now, to enable us to see the extent of this potential, we follow just 2 boys.
Dark,
What's happened?
It's gone from yellow to red now, getting
Dark
onto
red.
black.
What happened first of all?
Went like red.
Crept up from the bottom, started bubbling at the bottom. Gradually crept up and then changed colour to red.
I don't think that was the first time it was molten.
What, in today? No. No, it wasn't. It was molten right at the beginning.
So it's molten twice?
Yeah, it's been molten all the way through. It's getting thinner
Gradually
now.
crept up, so...
But didn't you say just now it's liquefying?
Yeah, it seemed to go.
It's more looser.
Looser? But if
Yeah.
it was a liquid already, how can it get more loose
Well, you
than
can
a
get
liquid?
thick and thin liquids, can't you?
Well, which was this?
Well, this is getting thinner now.
It was thick.
Yeah.
When it first happened, it was thick.
It was a powder, sir, then it
Yeah.
gradually crept up from the bottom.
Well, look, I think you can get another test tube and try this again.
Right.
All right? I'd like to see you do it more carefully. I think perhaps you may have rushed into this. All right, get another test tube and see.
Seems strange, and he's saying heat it more gently. You know, there must be a reason for it. I thought it'd be better to heat it strongly. I don't know why. Because if you want something to react, usually add a lot of heat to it.
Right, this is the second one, is it? Yeah. Now, if you do it very, very carefully, you'll notice something very interesting, but you'll have to do it carefully to see it. Don't overheat it. Hold it up a bit, that's it. Keep flicking it. What's happening?
Begin to liquefy.
Dissolving.
Yes, now supposing you upended that tube, what would happen?
Go straight in there.
Yeah, I should think it would. Never mind, carry on heating.
It's going darker red.
Now what's happened to it? Have a look at it now. Turn it upside down. Go on, quick. Up, right up. What's happened to it?
It's solidified.
Well, have you let it cool down?
No.
No.
And yet it's gone solid while you're heating it.
It's gone from liquid to solid then. Back to solid. Back to a
Well,
solid.
is this surprising or not?
Yes.
First of all, it went liquid. And then even though you were heating it more strongly, it thickened up almost to a solid again. No, is this surprising?
Yeah, yes.
Well, what might be happening to this sulphur? What caused it to thicken up again, do you think?
Something to do with the atoms, sir.
Yes, you see, before we had that model, didn't we? Let's have another look at that.
Steve, you tell the
Here we are. So this pattern. Now, what do you think's happened?
Might have intermingled.
What do you mean by intermingled?
Caught. One may have got caught in there. You know, it's...
How'd they get caught, do you think?
They block like we was doing on the board.
Well, no, what do you think? What do you mean by got caught?
Might have broken.
Might have broken, yes. So this could break open like that, and then what would happen?
Another one would come in.
Well, you get another molecule doing what?
Joining them to that.
Yes, you might easily,
Anyway.
mightn't you? Yes.
So it changes the atoms, the grain was.
Well, not so much the grain, but it changes what? It's changed the structure.
Yeah.
Yes, okay, right, carry on.
Yeah. Well, you know, you felt pleased because you had done something which most people hadn't done. Well, even 50 years ago, scientists were just doing.
The continual development of purposeful imagination at this level is the object of Nuffield Stage 2. It can lead to a deeper understanding of the nature of matter and the ways of controlling it. There can be no rigid formula for teaching this way. There's no easy solution to the difficulties of stimulating curiosity and imagination and keeping them alive. To do so requires time, which is provided in the Nuffield approach. One thing is certain, that pupils taught this way will be required to face problems with a critical and inquiring mind. And even those who do no chemistry after leaving school will have this experience behind them. Perhaps that's our greatest challenge. To develop in pupils a critical and inquiring mind. This may stay with them, even if much of the factual side of chemistry is forgotten.